Hello and welcome to this new short discussion where we discuss some papers, and here in particular, this is a paper in physics that has some things to say on the connection between, let's say, uncertainty relations in general theories and thermodynamics. So let's have a look at it. So first of all, this is here a paper that was published in 2013, so it's more than 10-year old. And you could say, but why, why do I talk about it? Well, first of all, why talk only about recent articles? There are thousands and thousands of papers in physics, just in physics, coming out every single year. And so obviously many of them that are insightful do kind of pass unnoticed. And I think this one is one of them. So let me just increase a bit more here. So this article was published in Nature Communication, and this is a theoretical paper, and its title is "A violation of the uncertainty principle implies a violation of the second law of thermodynamics." And you see that this is very fascinating indeed, because if you it ties essentially uncertainty principles to to the law of thermodynamics, to the laws of thermodynamics, and in particular the second law of thermodynamics. So let's start to see a bit what they are exactly doing. So first of all, so that's a general kind of introduction here. They want to put forward three ideas that are essential to the claims they're making. So first of all, they want to define what they call general theories. And general theories is essentially anything that is described, as is written here, by a probabilistic framework that makes the minimal assumptions that there are states and measurements. Essentially, that's kind of what you need to remember. It's a probabilistic framework that makes the minimal assumptions that there are states and measurements, and you try to formulate this in practice. So essentially, a state is going to be called rho. So the state is rho for people who are using quantum mechanics formalism. That would be, let's say, psi, the wave function. That could be rho, the density matrix in quantum mechanics. So that can be any kind of state you can imagine. And then this particular state is associated to what is called an effect. And these effects are essentially associated to the probability of a particular outcome of an experiment to come. Okay. And so what they are going to do is that what a measurement is going to be, so that the E here, and that's going to be the collection of all possible effects coming out of the experiment, and whose sum of probabilities given the given state of the system is one. So that's traditional kind of probability theory, but adaptable to classical and quantum descriptions. And in fact, that goes beyond that, because you could entertain the idea of having other ways of doing probabilities that do not, let's say, agree with the classical Kolmogorov theory of probability theory or the von Neumann quantum theory. Then what they do, so that's the first aspect. Then the second aspect is uncertainty relations. So here, the only thing they say is that if basically the outcomes of a measurement are twofold, so there are only two possible outcomes, then essentially you can put forward what are called, I think this is fine-grained here, uncertainty relations. That doesn't mean that the traditional uncertainty relations can't be retrieved, but here this is again related to fine grains, and so what that means is that it pertains to the exact outcomes of the experiments, and you try to formulate this in terms of the sum of probabilities of outcomes of two different measurements. Okay, so that usually is going to take that particular form, and this has to be less than or equal to, and in fact, 0 or 1 here, squared. So one of the things that comes out of it is that if this particular object here is less than 1, then you're going to have this particular uncertainty appearing, that exactly the state of an object, the probability is going to be one, or the state of the outcome, sorry, that is going to come, then the probability is one, and then consequently the other variable becomes probability less than one. Okay, so that's the kind of thing to be put forward, and that's what these uncertainty relations are about. And they give an example in the traditional spin systems that people have been playing with for a while now in quantum mechanics. And what they show is that if you have a particular state in general for a spin system, if you start with a so-called pure state, then if you add the probability of being, let's say, 0 in the x state and 0 in the z state, then it has to be less than or equal to a half plus a half over root 2. Okay, so you see that this is actually less than 1. So that's the kind of thing that tells you that there is a fundamental uncertainty, which is due to the commutation relations between these variables. So I'm not going to go into much details. This is a bit technical, so if you've got some background in quantum mechanics, quantum information, then this is going to be relatively easy to follow. If not, then please let me simply talk through it and try to go a bit past the jargon. So the bottom line here is that they're able to define what they call a fine-grained uncertainty relation that is supposed to hold in quite general cases. And then there is the second law of thermodynamics. I'm not going to, I mean, this is not a very technical part. It just says essentially that basically there are two multiple formulations that can be put forward. One of them is usually that the entropy of an isolated system can only increase or remains the same, but there are also plenty of alleged equivalent formulation. One of them being, and that's the one that they tend to focus on, that there cannot exist a cyclic physical process with a network gain of a cycle. And that's kind of what they look at. So what they actually work through is they derive a general theorem, um, and that is actually put forward here. And I'm not going to explain in details again. This would go kind of too much in the nitty-gritty details of the paper. If some people actually want that we discuss this part more deeply and in details on the board, then by all means do let me know, and I will be happy to do so. But the bottom line is that, and that's actually at the top here, the uncertainty relations would lead. So let's start with the phrase here. We give a strong argument why quantum mechanical uncertainty relations should not be violated. So there is really this idea, for example, that you could violate the uncertainty relation with respect to position and momenta, in the sense that maybe you could actually have the product, for example, of the two uncertainties that is less than h bar. And what this thing suggests is that no, because if that was the case, then essentially that would violate basically the second law of thermodynamics by enabling an impossible machine as per the second law of thermodynamics, which could extract network from a cycle. So that's really, really important. And the result, importantly, extends to more general theories than quantum theory. So this is not only um, for uncertainty relations that would come just out of quantum theory. That's for any kind of general theory. And that's really, really a very powerful result indeed. So I think this is a very interesting paper. Of course, you can look through more of these things, but the bottom line here is really that the idea is that there is, if you violate the uncertainty relations that we always try to violate in some sense in the technological applications, well, then you would actually violate the second law of thermodynamics. And so you could perhaps infer from it that basically the thermodynamics framework, in a sense, constrained the kind of theories that are allowed, and therefore the kind of things you can say about uncertainty in these particular cases. Now, it of course put together again the strong relationship there is between information and thermodynamics. So basically, that's it for that paper. I will put the link in the description of the video, and otherwise, see you in the next video.